Hello and welcome to a Ginger Mathematician video. So today is something slightly different. So we're focusing on IB maths here, specifically SLAA, so the standard level analysis and approaches. And this is going to be an all of topic 1 number and algebra video. So I'm trying this out for the very first time. So I'm going to go through each of the points in the syllabus, so SL 1.1, 1.2, as we go through and do a detailed example or question of each, so you know that you've actually covered that point in the syllabus. Again, if we're looking for more detail on any of these different points, that's a video certainly I can do in the future. Again, this is a new kind of video, so I'm very interested to see how it goes. Right, let's get started. So we've got SL 1.1 here, and the thing that you need to know for this is essentially standard form. So it's a times 10 to the power of k. This is often written in the standard form, scientific notation. And you need to be able to work with that, both non-calculator and calculator. Generally today I'll focus on non-calculator questions, but there is something on compound interest a bit later which you'll need a calculator for. So what kind of question comes up, what kind of IB style question comes up based on this topic? So here's question 1. So we've got a is equal to 8 times 10 to the power of minus 99, b is equal to 5 times 10 to the power of minus 98, and you need to write the following in standard form. So notice this is exactly in the IB format. So the first thing we need to do is do a times b. So to answer that question, we take 8 times 10 to the power of minus 99, and then we multiply that by 5 times 10 to the power of minus 98. Now multiplying and dividing with standard form is usually pretty straightforward. We take the numbers, so 8 and 5, we multiply them to give us 40. And then remember our rules with indices. So if we're doing 10 to the power of minus 99 times 10 to the power of minus 98, we're adding the indices together. So we get times 10 to the power of minus 99 plus minus 98. And that will leave us then with 40 times 10 to the power of minus. Now again, you could use a calculator for this to help you, but this is going to be the minus 197. However, this is not in standard form. At this point, you only get 1 mark out of 2. We need to convert this into standard form. And remember, 40 is not between 1 and 10, so we need to make sure that is. How do we do that? Well, we can divide through by 10. So that is equal to 4. But whatever we do to one side, we need to do to the other to make sure it's the same number. So we need to multiply this by 10 to the power of 1. If we do that, then we're going to get minus 197 plus 1. And that gives us 10 to the power of minus 196. So do watch out for that. That's the kind of little tricky question they could definitely put in an IB exam. Now with part B, again, they've made these numbers very big on purpose because now we're doing B minus A. So you can't really just put this into your calculator if it was on a paper 2. So we have 5 times 10 to the power of minus 98 minus 8 times 10 to the power of minus 99. And the key strategy with adding and subtracting with standard form is we want to make the indices the same. So we want to make these numbers the same. Now you can do it in 2 different ways. You can change one or you can change the other. Notice what I'm going to do in this particular question. What I'm going to do here is I'm going to divide this by 10. And again, we have to balance this out like in the previous question. So I'm going to multiply this by 10 to the power of 1. Now, let's see why we're doing this. So we have 5 times 10 to the power of minus 98. That stays as it is. Remember, 8 divided by 10, that's just going to be equal to 0.8. And by doing times 10 to the power of 1, we do minus 99 plus 1. That gives us 10 to the power of minus 98. We've achieved our objective. Notice now both are in terms of 10 to the power of minus 98. That makes our life much easier because all we need to do is subtract these 2 numbers from each other. That then gives us 4.2 times 10 to the power of minus 98. Is that in standard form? Yes, it is, because this number is between 1 and 10. All good, and then we've got our full 3 marks. Notice if I did the same idea here and say change this one, so this one here to 10 to the power of minus 99, which you can also do, you'd get 50 times 10 to the power of minus 99, but then it wouldn't be directly in standard form, and then you'd have to adjust it. So it takes a little bit of experience. Again, if that went a little bit too fast, that's absolutely fine. Again, go through this video nice and carefully, nice and slowly, stop, repeat as you need to do. So that was SL 1.1. Now we're going to go into SL 1.2, which is quite a big section. Again, I'm only doing one question per section, but just be aware we have arithmetic, sequence, and series. So essentially sequences or series involving adding and subtraction. Again, using the formulae from the formula sheet and the sum of the first n terms, so knowing that formula from the formula sheet. Using sigma notation, which I will talk about, I think, SL 1.8. So I'll look at that anyway when we look at converging infinite geometric series, applications, and then analysis. So yeah, I'm trying to fit as much as I can within one video. I don't want this to be too long. Again, give you a really good summary. So the question I'm going to do is a fairly detailed question here. So the sum of the first 5 terms of an arithmetic sequence, notice I'm always underlining as I'm going through. So we've got sum, first 5 terms is 50. The sum of the next 5 terms is 200. That's the important word, next, is 200. Determine the first term of the sequence. Now in IB notation that will be U1. Some teachers will teach this as A. And then the common difference, which is equal to D. Okay, so this is where we need to start from. The sum of the first 5 terms of an arithmetic sequence is 50. So we don't know what, I'm going to use A and D. I don't know what A is and I don't know what D is. As soon as I get the sum of an arithmetic sequence, I'm going to write down the formula. This comes from the formula sheet, so we get n over 2, 2a plus n minus 1d. Okay, so the sum of the first 5 terms is equal to 50. So that means then S5, so the first 5 terms. So we've got n 5 over 2, n is 5 here. We don't know what a is. We do know what n is, so that is equal to 5, so 5 minus 1. So I'm copying down the formula, putting in the values of n that I know, and we're told that this is equal to 50. Okay, now the next thing that we can do is the sum of the next 5 terms is equal to 200. Okay, can we use that in some way? So notice if we have the sum of the first 5 terms is 50, and then the sum of the next 5 terms is 200, the sum of the first 10 terms has to be equal to 250, those two added together. So S10 will be 10 over 2, 2a plus, n is 10, so 10 minus 1, d, and that's going to be equal to 250, because first 5 terms is 50, next 5 terms is 200, so the sum of the next 10 terms together is 250. Okay, let's see if we can tidy this up a bit. So 10 over 2 is 5. We have 2a plus 9d is equal to 250. Okay, here we can simplify this further by dividing by 5 on both sides. So let's do that. That cancels. Notice this is why we don't always expand brackets immediately like you do, say, IGCSE. You see a bracket, you expand it, but sometimes you need to be a little bit more careful. So we've got one equation, 2a plus 9d is equal to 50. Now let's see if we can tidy up the S5 one. So if 5 divided by 2, that's 2.5. We have 2a plus 4d, and that's equal to 50. Okay, I can divide by 2.5 on both sides. Now again, you might have to do this manually if it's non-calculator. For the benefit of this video, I'm just going to do this on my calculator. So I've got a CG50. This is what I tend to recommend these days. You'll see in other videos I use TI Inspire as well. That is also perfectly fine. So if we do 50 divided by 2.5, we then get equal to 20. Okay, so now we've got 2 equations with 2 unknowns. Again, you should be familiar with this from either MYP or the IGCSE course. We can now actually solve these. So let's write down these equations. So 2a plus 9d is equal to 50. If you're liking this video, of course, then please do give us a like and subscribe. Help support the channel and lets me know essentially if you want more IB content. Yeah, and this is SLAA. Of course, there's always room to be doing AI content as well. Actually, the course I have the most experience with is actually AIHL, interestingly. So if you want me to do some content on, say, eigenvalues, eigenvectors, please let me know. Now, the easiest way of solving this, making sure we've copied this across properly, is we can subtract one from the other here, which is fantastic. 2a minus 2a disappears. 9d minus 4d is 5d, and 50 minus 20 is 30. Therefore, d is equal to 6. So now d is equal to 6, then we can work out the first term here. So let's just take any equation that we have. We can take this one here. So we can substitute back into this equation. Let's call this like 1 and 2. We sub in equation 2. That means then that 2a plus 4 lots of 6, because d is 6 here, is equal to 20. Therefore, 2a plus 24 is equal to 20. Again, you can solve this in lots of different ways. I tend to use this arrow idea, doing opposite operations, so minus 24 on both sides. That gives us then 2a is equal to minus 4, and therefore a is equal to minus 2. So our answer here, again, like to be nice and clear for the examiner. So our first term is equal to minus 2, and the common difference, so being really clear here, is equal to 6. And that gives us all 6 marks on this question. Often quite generous at IB, I find, in terms of giving you marks for this. But again, there's a lot of content to cover, so again, it's always, okay, they reward you for the work that you have done. Okay, on to SL 1.3. So now we're looking at geometric sequence and series. So that means then with a sequence, we've got some multiplying or dividing involved. Again, using the formula on the formula sheet for this and working out the first n terms. In sigma notation, again, I'll talk about that. I think SL 1.8, if I remember rightly, and applications as well. So the question I'm going to choose here, which is a very typical IB question, they like these kind of questions, is they give you a sequence with some x's in a variable, and then they tell you it's geometric or arithmetic, and then you have to work out x. Okay, so we've got our first term here. So I usually call this a or u1. Then the next term will be a times r, and then the next term will be a r squared. And remember that the way you can actually work out the common ratio is dividing one by the other, because we're multiplying by something here, and then we're multiplying by something here. So to work out the common ratio, well, that has to be equal to either the third term divided by the second term, or the second term divided by the first term. So either x plus 7 divided by x, so essentially ar squared divided by ar, or we can do the second term divided by the first term, which is x over x minus 3. Notice this actually gives us an equation to solve, because these two things are actually the same. And at this point, we just have an algebraic fraction to solve. So the easiest way of doing this, I like doing what's called cross multiplication. So this times this, this times this. That means we get x plus 7 times x minus 3 is equal to x times x, which is x squared. Okay, notice there's only one value of x. That's always something to look out for in a question. So there won't actually be either there'll be a quadratic with the same value, or it'll just be one answer. So keep that in mind. So we just expand the bracket here. So we have x times x is x squared. Again, this is our normal FOIL procedure. X times minus 3 is minus 3x. 7 times x is plus 7x. And then plus 7 times minus 3 is minus 21. And the great thing is here, the x squareds we have on both sides, so we can cancel, which is fantastic. Then we have minus 3x plus 7x, that's 4x, minus 21 is equal to 0. And out of all of this, suddenly we've actually got a really straightforward equation to solve. We add on 21 on both sides. If we do that, that cancels, giving us 4x equals 21, and then we divide through by 4. So x is equal to either 21 over 4, or we can write this as a decimal as 5.25 to give us our 5 marks. Now I have, in terms of putting the marks on here, made it as if it's an IB question. So they do reward you quite a lot for these, as I said in the previous question as well. So putting these together, SL 1.2 and 1.3, these are two very typical questions, working with either arithmetic or geometric sequence and series. Knowing the formulae and knowing how to manipulate them as well is really important. Okay, on to SL 1.4, which is now definitely calculator used here, and we're going to be looking at financial applications of geometric sequences in series. So essentially either compound interest or annual depreciation. Now you do need to know how your calculator works, particularly the finance solver. I don't think we're looking at a finance solver question specifically here today. We're going to use the formula from the formula booklet instead. But if you do have a calculator, you need to know how your individual finance solver works, whether it's the CG50, so this is the one I'm using here at the moment, or the TI Inspire. Again, please let me know in the comments below which calculator you're using. You may even use a TI-84, which is a bit more irritating when it comes to these questions. I certainly would go with one of these two if you have one at home. But I can make an individual video on using the finance solver. So the question we're going to do here is as follows. So Chiara here, she invests 50,000 euros in an account that pays an annual interest rate of 3% compounded over 6 months. This is where it differs from, say, an IGCSE or NYP problem. Determine the value of the investment after 2 years, rounded to the nearest cent. And usually very clear about how they want it rounded. So you need to know the following formula. So present value is equal to, final value is equal to present value multiplied. This is where the formula changes from, say, IGCSE. So 1 plus r over 100k to the power of kn. Now, what do all these things stand for? So PV is the present value, so what it currently is. Let's write this down quickly. If you know this already, skip on the video. R is the annual interest rate. So interest rate. N here is the number of years. Now we're doing this without a calculator. As I said, most of this is non-calculator here. And K is the compounding per year. So these things have to link together. Okay, so for this question, let's break this down. So the present value, so PV, Chiara has 50,000 euros. Our annual interest rate is at 3%, so R is equal to 3. The number of years is 2. And the compounding per year, so every 6 months, so it compounds twice in the year, so K is going to also equal 2 as well. Once you've established this, and when you do an IB question, you should write it like I've done. What's PV, what's R, what's N, what's K? Because for more complicated questions, maybe they want you to work out the annual interest rate, or how much is it compounded. So you write down what you have, then you think about how we're going to work out what we need to do. So final value is equal then to 50,000. Then we have 1 plus the interest rate, R is equal to 3. And we have 100k, so 100 times 2. And then to the power of kn, so that's 2 times 2, which is just equal to 4. So we set it out very neatly and very nicely. And now it's just a calculator exercise. Generally, it's going to be very hard to make this non-calculator. I'm sure there's a way. Make the numbers really, really nice or something like that. So I put all this in. I get 53,000. Again, they want this to the nearest cent. What I generally do on the safe side in exams, I write down 177 ... So if I make a mistake right at the end, I'm not going to lose more marks than I should, just lose 1 mark. So if we round this, we have 53,068 and then 18 cents. Make it really clear what your answer is here. Again, they give you lots of marks for this, but they do want you to write the working. Say I made a mistake and put R as 2 rather than 3, for example, but they've seen everything else that I go through, you're going to minimize the amount of marks that you lose. Okay, on to SL 1.5. So this is now the laws of exponents with integer exponents. That's the kind of easy stuff. And also working with logarithms as well. So logarithms with base 10 and base e. So you have to know what the natural log of x is, e to the power of x, so the exponential function. And then using technology to actually numerically evaluate that. So you can often use graphing as well. I often recommend graphing rather than using nsolve and things like this. Again, I can talk about that in a later video on the calculator part. So what we're going to do is we're going to be solving an exponential equation. So a reasonably tricky one here. So this is generally a non-calculator question. We want to solve this equation. And the first thing I'm going to notice with an equation like this is that we have a 9, a 3, and a 27. They're very specific numbers. Specifically, 9 is equal to 3 squared and 27 is equal to 3 cubed. So they've set this up where they're all powers of 3 in some way. So the first thing I'm going to do is going to write everything in terms of the power of 3. That means 9 is 3 squared, so 3 squared to the power of minus x is equal to 3 times, well, 27 is 3 cubed. So I'm going to write down 3 cubed. That's all I've done here. I haven't done anything else. All I've done is replace 27 with 3 cubed, replace 9 with 3 squared. Now, what do I do at this point? Well, I can now use my indices rules. So remember, if you've got a power of a power, we can multiply these together. So 2 times minus x is 3 to the power of minus 2x. Remember, 3 itself is just 3 to the power of 1, but I'll come back to that. And here we do the same thing. Notice we need to think of this as a bracket. So if we're multiplying the 3 by 2x plus 1, we have to multiply both aspects of it. So that means we get 3 to the power of, well, 3 times 2x is 6x, 3 times 1 is 3. And now just to tidy this up, notice our rules of indices. What can I do to combine these together? Well, I can just add the indices. So I get 3 to the power of 6x plus 4. Notice numbers add to numbers, the letters add to letters. Once I've done that, then I can actually compare coefficients. Now, that's a very complicated name for a fairly simple idea here, which is that if they're both raised by the same power, then this has to equal this. This is why we've taken this approach. You do a similar thing for logarithms as well. That means we get minus 2x is equal to 6x plus 4. And then back to a linear equation that's easy to solve. So all I'm going to do here is I'm going to minus 6x from both sides. Okay, this cancels. Not that cancels. Not that cancels. Minus 2x minus 6x is minus 8x. I got ahead of myself here. 6x minus 6x cancels. That means we have equal to 4. And then we divide through by minus 8. Again, we can tidy this up. Equal to minus a half, or for you decimal lovers out there, minus 0.5. Okay, on to SL 1.6. This is always a tricky one to kind of teach to students because the deductive proofs can differ. Again, we don't go into much detail at all. If you're doing high-level AA, I'm sure you know if you're a high-level AA student, you end up doing things like proof by induction, exhaustion, by contradiction. That's the one I'm trying to think of. Students often struggle to get their head around. But here we're just doing simple deductive proof. Okay, so we'll do a nice example of that. And that is that the proof that mean of 3 consecutive square numbers can never be an integer. Now, whenever you're doing a proofy-woofy question, as I like to call it, then we just need to identify these words. So first of all, the mean. So remember, that's just adding everything up, dividing by how many there are. 3 consecutive. Now this word consecutive, often students with not English as their first language can struggle. It just means one after the other. So 3, the 2 next consecutive numbers are 4 and 5. Yeah. Square numbers, again, I think that's fairly straightforward. So a number squared, so 5 squared, and can never be an integer. So an integer here is just a whole number. Now what students often struggle with is a structure to do these kind of questions. So I'm just going to take my first number to be x. I have no idea what it is, but I'm just going to call it x. I want to do 3 consecutive square numbers. So I have x. I'm going to have x squared because it's a square number. Then I'm going to have the next number, so x plus 1. I'm going to square that. I'm going to take the next number, x plus 2. And I'm going to square that. And what they're saying here is the mean of those numbers can't be an integer. So what it's saying here is we've got x squared plus x plus 1 all squared plus x plus 2. So if we add up all these square numbers and divide by how many there are, so there's 3 numbers, so x squared, x plus 1 squared, x plus 2 squared, that apparently is not going to be an integer. Now don't worry about that part. Usually it becomes straightforward or obvious when you get there. I say that here, yeah? So first thing we do, we've got brackets, so let's expand some brackets. Now you're thinking, expand brackets, there aren't brackets to expand. Well, remember, squaring is timesing by itself, so it's x plus 1 times x plus 1, and x plus 2 times x plus 2. Again, all over 3. So let's do some quick expanding. Again, I'm just going to speed through this. I'm sure many students at home speed through it on 2 times speed. So we have x squared plus 4x plus 4. Watch out if I make a mistake, obviously. Over 3. Okay, let's pop it over here so my camera is not in the way. So how many x squares do we have? Well, we have 3x squared. Let's add up the x's. So we have a 2x and a 4x. That's a 6x. And the numbers is equal to 5 over 3. Okay, well, we can simplify this through. We have to be careful how we simplify. So 3 divided by 3 is 1, so we get x squared. 6x divided by 3 is 2x. And then 5 divided by 3 is just 5 over 3. Okay, so why can this never be an integer? Well, notice if you've got any number, remember it has to be a whole number, so 2 or 4, we're always going to be left over with this 5 over 3 remainder. So whatever integer we have, whatever number that we start with, we're always going to have this 5 over 3 left, which then makes it not an integer. So we're always going to have a remainder of some shape or form of 5 over 3, and therefore not an integer. So with these kind of questions, it takes practice, first of all, but also not trying to get too far ahead of yourself. So what I mean by that is, okay, look at the question, see what they've written down. Okay, can we work with that algebraically in some way, with x's or y's or whatever letter you want to use, and then see if something pops out. I mean, as soon as I saw this, I'm like, well, we're always getting a 5 over 3. It doesn't matter what whole numbers these are, we're still going to get this 5 over 3 left, this remainder, as I like to call it, and therefore that shows it can't be an integer because it's not a whole number instead. Tricky kind of question, but again, if you want more detail on me doing a proof video, then again, please let me know. This is a good way of me testing the water of what topics that you need. Okay, on to SL 1.7. So it's a big topic and therefore it's going to be a big question. So working with rational exponents. Again, we looked a bit of that earlier on. The laws of logs, so that's important here. And again, one of the topics that students often find most tricky, particularly at the start. And of course, using the log law here specifically and the change base rule as well. So I'm going to try and include all of this in a really tough question, and you're probably going to think by the end of the question, how do you even see these things? And the key thing to realize really with these questions is you take what you have, you see if you can manipulate it in some way, and then the answers will kind of fall out to you, and we'll see what I mean when we go through this. So first thing here, the first part, is write this particular expression in terms of log 3 base 6, and then using that somehow, and again it's not going to be obvious how we use that, we're actually going to solve this equation over here, and we're going to write it in terms of log 3 base 6. It has to have something to do with part A. Okay, so let's have a look at part A. So the left hand side here, LHS is how I usually call it, is log 3 base 2 over 1 plus log 3 base 2. Now, how are we going to change that in terms of log 3 base 6? So the first thing that comes to mind here is try and tidy this up at the bottom, so make it one logarithmic expression. So the way we can do this, we can actually change 1 itself using what we have so here is actually to log 2 base 2. Remember, if the base is the same as the number in the log, then that's equal to 1. So I'm going to use this idea, one of our log laws. And remember, if we're adding logs, it's the same as multiplying numbers, so I can then rewrite this on the bottom as simply with base 2 as my log, 2 times 3 is 6. So one of the benefits of logs, it helps you solve exponential equations, is I can actually use addition here and multiply what's in the log. Now once I've got this expression, so log 3 base 2, let me write it again over here, like so. Is now going to use the change base rule both on top and bottom. So at the moment I've got log base 2 and I want log base 6. So the way I remember this rather than go to the formula directly is I'm going to write this as log 6 top and bottom for the first part. The number there originally, so 3 goes here, and the base number here 2 goes down here. This is the way I remember. And then we have log base 6. Again, we can do the same thing, set up my fraction. The initial number 6 goes at the top, the 2 here goes at the bottom. Now it looks a bit more messy, but actually lots of things simplify. Remember the first thing I mentioned, which is log 6 base 6, the two numbers are the same, therefore that just simplifies to 1. And notice we have a log 2 base 6 top and bottom, so that means we can cancel that. And actually this just becomes then, I've just put LG, no, not LG, no, don't do that. That's another notation A level for log base 10. Then we just get log 3 base 6 over 1, and that's just equal to log 3 base 6. So actually these two expressions here are equal to each other. That's going to be very helpful for us in part B. Now look out for this, hence or otherwise. They love this kind of language, which means there's going to be something in part A that we can use to help us solve this equation. So let me rewrite this equation, and whilst I'm doing that, you can like the video if you've got to this point and you've been suffering with logs and you just need a bit of clarification. And notice we need to write it in terms of log 3 base 6, so it needs to be something related to part A. Okay, so the first thing that comes to mind here is I want the bases to be the same. That's always one of the first thoughts that I look at here. So the way I'm going to do that is I'm going to use the change base rule on the log x base 3. I suppose I could do this both ways round, but yeah, I could do it either way round here, but I'm going to do it on log base 3. So that means I'm going to write out my fraction. I want my new base here to be 2, top and bottom, so it's the same as this base. The initial thing, so x goes here, and then the base then goes here. So all I've done is I've rewritten it in this form. Okay, at this point I've got a common factor of log x base 2, so I can take that out and then put the rest in brackets. So what do I multiply log x base 2 to get log x base 2? Well, just 1. And then I've taken a factor of this out, so I can put 1 over log 3 base 2. And that's now equal to 1. Not entirely the bracket looks like what we worked with before, but we can certainly do some work on this. The first thing that comes to mind here is actually try and make a common denominator. You do this a lot in algebraic fractions back in IGCSE in the day. So I'm going to rewrite 1 here as just log 3 base 2 over log 3 base 2. So the same thing top and bottom. Again, this is a trick that you often see in algebra generally speaking. And that means I can just add the tops. So I can get log base 2 outside. That means I can just add the tops. So I get 1 plus log 3 base 2 over log 3 base 2 is equal to 1. So you look at this and go, oh, well, it's not exactly the same. Mr. Gower, what are you doing? It's not exactly the same as what we have here, yeah? We've got log 3 base 2 over 1 plus log 3 base 2. And this is like the wrong way round. But notice it's just a reciprocal, yeah? So I can use this fact and go, well, if I flip that, 1 plus log 3 base 2 over log 3 base 2, well, I can just flip this as well. So I can just write this as 1 over log 3 base 6. I'm just using the reciprocal on both sides. Very, very sneaky. So I can just replace my bracket here, log x base 2, with 1 over log 3 base 6 is equal to 1. And actually this makes things a whole lot easier because I want to try and get this on its own. So what's the opposite of, timesing by 1 over log 3 base 6? It's just timesing by log 3 base 6 on both sides. You probably feel the difficulty going up here in this video and this part of the video. So this cancels, which is the whole point. So we get log x base 2, and then we just times this, so we get log 3 base 6, which is what we're looking for, in terms of log 3 base 6. And now, this is the way I generally teach this, we can just write this as an exponential statement. So notice we can have 2, this is our base, so 2 to the power of whatever's on the right-hand side, so log 3 base 6 is equal to this part, x. This is just the definition of a logarithmic statement. And notice the answer is now just dropped out and given us all 6 marks for this question. Again, definitely you can feel the difficulty level rising. Again, this is a top end SL, obviously HL is probably a medium star question, but it shows you how confident you really need to be with working with logarithms. Okay, on to SL 1.8, it's like a little tiny extra section here, which is specifically infinite convergent geometric sequences. Specifically this formula, so S to infinity is equal to A over 1 minus R. Of course, we need to make sure that we're following this condition that the modulus of R is less than 1 when we use this formula. So I did promise you some sigma notation and it is here. So we need to find this value. If you don't like this notation, I can write this a bit more normally. So we should have 3 over 4 to the power of k. Now, when students get confused with sigma notation, what I like to do is just write out the first few terms. So when k is equal to 1, that just gives us 3/4. And then we're going to have, when k is 2, so 4 squared on the bottom, which is 16, 3 over 64, and so on. So it goes on like this. Now, the great thing about writing it this way is really obvious, I hope it's really obvious, to actually work out your first term and a common ratio. So the first term here, the first fraction, is just 3/4. What are we multiplying by each time here to get the next number up? Well, we're multiplying by 1/4, yeah? Again, you can check that and see, okay, yeah, the top's staying the same, but the bottom is multiplying by 4. So our common ratio here is equal to 1/4. Once we know that, then we can use the sum to infinity formula. Notice here, r is 1/4, so that's less than 1 and more than -1, so all is good. So we can use this formula, a over 1 minus r. That means we have 3/4 over 1 minus 1/4. Well, that's just 3/4 divided by 3/4, which is a nice easy thing to work out, and so the answer is just equal to 1. So that means this sequence, if we go on infinitely and add all these fractions together, we're going to get to 1. Super, on to SL 1.9, so the very last point of topic 1 number algebra, and that is the binomial theorem. It's a biggie, it's one you really need to know well. So specifically being able to expand a plus b to the power of n and various things within that, and using Pascal's triangle at NCR. Sometimes we're using technology, sometimes not. Generally this tends to be a paper 2 style question, but it doesn't have to be necessarily. Right. On to question 9, so full 8 marks here. So in this expansion, so ax plus b to the power of 5, fairly tricky question. The coefficient of x to the power of 4 is equal to 15, and the coefficient of x squared is equal to 270. And from this information, we need to work out the values of a and b. So we're looking for very specific terms here of this. Okay, so we want the term then for the first one of ax to the power of 4. Remember that we're doing the power of 4 of everything here. And that means the power of b needs to be b to the power of 1 because these indices have to add up to 5. The key thing is working out the binomial coefficient beforehand. Well, it always starts with 5 because there's 5 to choose from. We have 5c, and then we just have to work out, okay, which number are we looking at, 4 or 1. It doesn't actually matter, but we generally take the one here next to the a, so we're looking for 5c4. So this coefficient, so the 5c4 part, this should add up then to 15x to the power of 4. That's what this question is essentially saying. And we do a very similar process here with x squared. So we want an ax all squared. That means the power of b needs to be 3, because 2 plus 3 is 5. And then what binomial coefficient? Well, we start with 5, and we have a 2 here, so we want 5c2. Again, the symmetry of Pascal's triangle means you could take 5c3 and 5c1, but we try and keep it very straightforward. And that means we get 270x to the power of 2. So we can use the calculator to work out 5c4. You can probably use the formula as well. On these calculators, it's a pain to find. So on my graphical calculator, again, it's got the CG50. I always find this is a complete pain to do. But essentially, we go to Option, then we click on F6 to go through to Probability, because we often use this in probability questions. And then we go to NCR. So then we want to work out 5c4. So 5 NCR button 4. Okay, that's just equal to 5. Useful to know this process. So we have 5 a to the power of 4 x to the power of 4 b is equal to 15 x to the 4. Again, we can do a similar thing with 5c2. So we go 5 NCR button, that's F3, and then 2, that gives us 10. So we get 10 a squared x squared b to the power of 3 is equal to 270x squared. Now we're going to do this idea of looking at coefficients here. Again, we saw that in the previous question. So it basically means that if we take this highlighted part, so the bit without the x to the power of 4, then this needs to be equal then to 15, and then we can do a similar idea here as well. Okay, I love the highlighter here, really makes things clear. And so we can actually make a difficult looking equation out of this. So we get 5a to the power of 4b is equal to 15. That means then a to the power of 4b is equal to 3, divided by 5 on both sides, and then we have 10a squared b to the power of 3 equals 270. Divide through by 10, so we get a squared b to the power of 3 is equal to 27. And on first sight, it doesn't look like that easy to actually solve this set of equations. Again, there's a couple of different ways you can do this, but there's a sneaky little trick here. So what I'm going to do is actually going to cube both sides here. So I'm going to put a little square to indicate that we're cubing both sides. So if we do that, a to the power of 4 all cubed is a to the power of 12, b cubed is b cubed, and then 3 cubed is 27. Now, why have I done this? So notice we've actually got 27 on both sides, which is kind of useful. So if I take this equation, a to the power of 12, b cubed is equal to 27, I can actually divide one by the other here to actually work out and essentially eliminate the b cubed. So if I divide this, a to the power of 12 divided by a to the power of 2, that's a to the power of 10. B cubed divided by b cubed is just 1. 27 divided by 27 is just 1. So actually I get an equation, even though finding the 10th root of something is usually quite complicated, it's pretty straightforward here because a is just going to be equal to plus and minus 1. Notice we have to be careful, we have an even exponent, even power, even index, therefore it could be plus or minus 1. However, when we substitute it back in, so if I substitute it into this equation, so sub in equation 1 here, it makes no difference if it's plus or minus 1 because 1 to the power of 4 minus 1 to the power of 4 is still just 1. Therefore, we get then b is just equal to 3. So a has two different values it can be, but notice we're working with these coefficients. Therefore, it doesn't matter if it's plus or minus because you're always squaring it or you're always to the power of 4. So two answers, a is plus or minus 1 and b is 3. Okay, it comes to the end of this fairly long video, so congratulations if you made it. If you'd like one of these kind of videos for topic 2, topic 3, or maybe you're doing IB HLAA, you're doing IB SLAI instead, and you'd like a similar kind of video going through syllabus point by syllabus point, then do let me know in the comments below. And if you're looking for perhaps the best IB Maths website ever out there, then check out the video right in front of you because Revision Village is going to solve all your problems.